some examples related to fully nonlinear first order partial differential equations. So in the previous lecture we had our nonlinear equation written in this form, where as f of a function of x, u, and p, where x is an n-dimensional vector, I use straight x for vector, u is function of x, and p is also an n-dimensional vector of all partial derivatives of our function u with respect to each independent variable x, right? So x are independent variables and u is the function we want to find, and we assume that both f and u have derivatives, continuous derivative up to order 2, right? And we also derived 2n plus 1 characteristic equations, which we called CE. They look like dx dt equals f with respect to p, deriv du dt is dot product of p and fp, and dp dt is negative fx minus negative fup. So now let's just do a computational example. When we have ux times uy equals u for positive x, and here to so we used for two-dimensional equations, for equations in two independent variables, we use notations x and y instead of x1 and x2. So here, to make connection between this and this general formula, x is related to x1 and y is related to x2. And p is derivative of u with respect to x, and q is derivative of u with respect to y. So in these notations, that would be p1 and p2, right? So, but now we have p, instead of p1 we have p, instead of p2 we have q. So these are notations. So now, how to write down our function f? It's written f equals 0, so we move u to the left, and using these notations, ux would be p, uy would be q, so we have f equals pq minus u. And now let's write down equations. So here we have n equations. In our case, it will be two equations. So first of them would be dx dt, and then we have to differentiate our function with respect to p. So we take this function, we differentiate it with respect to p, we will have q, right? And second equation would be the same, so dy dt, we have to differentiate now with respect to q. When we differentiate with respect to q, this equation, we have p. Right, we think of that as equations written in 2n plus 1 dimensional space, where we have all variables x, y, u, p, and q. So, and then, so we have these two equations. So this one equation, we have dot product, p and fp. So if we differentiate with this equation with respect to p, we will get q. So we'll have p times q. And plus must be second component of this first vector. This first vector is vector whose component is pq, right? Oh, sorry that p here, maybe it's bad notations, but p here is just maybe, I don't know, I should put here vector so it's not confusing. So p here is just p1 of this vector, and q here is p2 of this vector. So, and then we differentiate with respect to q, we will get p, so we have q times p. So we have here this dot product, and that's equal to pq. And then we have, so far we discussed two of these, one this equation, and we need to discuss these two equations, dp dt. And P here, again, P here is our vector, right? So then we will have, for the first component, we have, now for component, dp dt equals, when we differentiate with respect to x, no x is here, so this would be gone. And then here we differentiate with respect to u, we will get -1. And here we have negative, so we have -1, and must be multiplied by p. So p, now first component, the corresponding p, and that would be dp dt equals p. And then we do the same for the second component of this vector, that would be dq dt. Again, with respect to x is 0, and with respect to u is -1, and then now must be multiplied by the second component of this vector p, right? And then we will have second component is q. So here we have our set of characteristic equations. So now for these characteristic equations we need to derive initial conditions. So initial conditions here were given u at 0y equals y squared. So as usual we write x of 0s would be 0, y of 0s would be s, and u of 0s would be s squared. So we have this these conditions written in a way we've been writing them for quasi-linear equation. So now we need to write two more equations, two more initial conditions for p and q. And for p, we can derive it from this initial condition if we take it and differentiate with respect to y. So we differentiate this equation with respect to y, and what we will get? du dy, in our case it is q, so we will have q at 0s, and derivative of y squared would be 2y, so y is s, so we write 2s, right? But as I mentioned when we're discussing the theory, second initial condition we cannot get from here, so we need to use the equation. So our equation is f equals 0, so pq minus u equals 0. So we have this equation here. We can solve this equation for p, since we need condition for p, and p would be equal from this equation u over q. If we have u over q, now we want to find an initial condition p at 0, meaning 0 stands for our variable t. So at 0s, and that would be u. Condition for u is s squared, and condition for q is 2s. S squared over 2s, we will get s over 2. So now we got all of the initial conditions we have. They're all here in the red frame. So we have all of the initial conditions. Now let's start integrating characteristic equations, and we start from, say, the last equation. We'll go back. So this equation dq dt equals q, easy to integrate, and then it will be ln of absolute value of q t plus some constant, and then we take exponential functions from both sides and thinking of constants as function of s. So we have q equals f1 of s e to the t. And f1 of s we can find from initial conditions because we know that q at when t equals 0, we have 2s. So f1 of s equals to s, and that would be our final expression for q. Then we do the same for p. For p we have exactly the same equation, so when we integrate we will get p equals f2 of s e to the t, and then initial condition, we use initial condition to find f2, we have s over 2. So when t equals 0, we have f2, so f2 equals s over 2, and this would be our final formula for p. P equals s over 2 times e to the t. So now we are moving to our equation for u. Du dt equals 2pq, so we have du dt equals 2pq. Since we already found both p and q, now we multiply them. We have 2 and 2 are cancelled, s and s will give us s squared, and multiply by 2 it will be 2 e to the t times e to the t e to the 2t. I hope I corrected all of the typos that I previously had. And so when we integrate, right, when we integrate e to the 2t, we have to divide by 2. So 2 will be cancelled, and u equals s squared e to the 2t plus some function of s. And then we find this function of s using the initial conditions, right? When t equals 0, we have s squared, and we need to have s squared, so f3 is 0. And this would be our formula for u equals s squared e to the 2t. Okay, and we're moving forward for these two equations. So for the first equation, dx dt equals q. We already found q. Q equals 2s e to the t. So we integrate this. It will be 2s e to the t plus some function of s. And we use this condition. It must be 0. So when t is 0, we have 2s. So we have to subtract 2s. f4 equals negative 2s, so that would be our final formula for x. And similarly, we do computations for y. dy dt, here is our equation, dy dt equals p, and p is s over 2 e to the t, and then we integrate. We have f over 2 e to the t plus some function of s, and for y we're supposed to have s. So at 0 we have s over 2, so we need another s over 2, so then f5 equals s over 2. So that would be our equation for y. Right, so now what do we have? We have equation for u written in terms of s and t, and we have equations for x and y written in terms of s and t. So we got our parametric representation of the surface. So now we need to invert, to switch from s and t to x and y. So we take these two conditions, right, and solve for x, for s and t. So first I gave name to the first equation as E1, to this equation as E2. If we take E1 and subtract 4 times E2, we will get in the left hand side of the x minus 4y, and then in the right hand side we will have this term with t cancelled, and that would equals to negative 4s. And then we take equation E1 and add 4 times E2, and in this case we will get x plus 4y, and in the right hand side we will get, this term will be cancelled, and we will get 4s e to the t. And from here we can have expression for 4s, since we have it as 4s, and we have expression for s that we will need to plug into u. And then for e to the t, from the second equation, if we replace 4s with 4y minus x, for e to the t we will get x plus 4y divided by 4s, which is 4y minus x. So basically now we have everything we need to be able to write down the final answer. So we have our function u equals s squared e to the 2t, which will be s squared is 4y minus x over 4, everything squared, and e to the 2t would be x plus 4y over 4y minus x, and everything is squared. Now we can simplify. If we just cancel numerator and denominator here, then the answer would be u function u equals to x plus 4y squared over 16. So a special role in physics and calculus of variations plays a nonlinear equation when, or play different, maybe I can say, nonlinear equations when our function f in our general nonlinear equation does not explicitly depend on u. So there is no dependence on u. So instead of f, I will be writing h of x and p. And so our equation could be written in the form h of xp equals 0. And then let's look again at our characteristic system of characteristic equations. So now here notations the same as we used in n-dimensional case. So we have the x dt equals fp. So now instead of f we have h. So instead of f derivative with respect to p, we have h with respect to p. And then here du dt to p instead of f, I just put h. And then the third equation, we can see that for about the first term to be negative hx, but since there is no dependence on u, so this term will disappear. So we don't have this term here, right, in the last equation. And now, if we look at the first and third equation, they don't have u. So we can solve first the first and the third equation. So and then we will be able to solve equation for u. So equations here, I wrote this first and third equation, and they called Hamilton's equations. So they called Hamilton's equation. Then if we're able to solve this equation, then finding u, at least theoretically, is trivial because we will know everything. We will just have to integrate this equation. And this system is coming from physics, and it's used, for instance, in classical mechanics, and not only in classical mechanics. So then we can think of a simple example. So in physics, x usually stands for coordinates, p stands for momentum. So if we're thinking about a system, it could be classical mechanics, quantum mechanics. Generally, we can think about total energy. If we write kinetic energy and potential energy, and for instance, if we have a simple harmonic oscillator, right? If you have a spring and some mass, you pull the mass and you have oscillations, right? Here's kinetic energy. Keep in mind this example. Here's potential energy, and then if we replace v velocity with p. So in this example, let's think of one-dimensional case, right? So x is one-dimensional coordinates, p is our momentum. So momentum equals mv. So if we replace here v, instead of v, we will write p. then total energy written in terms of p and x, momentum and our coordinates, then this total energy then is called Hamiltonian, right? So then it's called Hamiltonian, and it can be written Hamiltonian for a system, and as I mentioned, it's used in both in classical mechanics and in quantum mechanics, so we can write Hamiltonian of the system is when total energy is written in terms of momentum. And then if we have this h here, then how we can write our Hamilton's equation for this. So then dx dt, x now is not a vector, just one-dimensional thing. What is HP? HP we differentiate will be 2p over 2m, 2 cancelled, so we have p over m. And the second equation, again we don't have vectors here, dp dt negative hx, and we differentiated with respect to x, so if we have it written in this form, it will be a negative derivative of potential energy, or if we have this where c is a constant related to the spring, right, when we to the materials, and then we will have negative cx. And now let's think of how this is related to physics. So what is the physical meaning of the first equation? So first equation, dx dt, when we think of t as time, then it just states that p equals mv. So it's basically this physical notion of momentum. And what is the meaning of the second equation? So if we have dp dt, just mentally let's replace p with mv, and we will have derivative with respect to t, we'll have ma, and this is f. So this is this just constitutes the second Newton's law. And as I mentioned again, so here I just wanted to show connections with the Hamilton's equation and with the Hamiltonian. So now let's consider another example. Let's discuss the eikonal equation. This equation related to wave propagation and to propagation of light, so it's related to optics and serves as a connection between waves and geometric optics. So also famous equation, and this is equation of the type we discussed when we have h of xp, so when there is no dependence on u. And this equation looks like this. So gradient u, gradient, it means we have derivatives, right? And models of derivatives is just we have all derivatives squared. As an example, just a specific example, let's solve Cauchy problem in the case of two independent variables, and also let's think of k to be generally it could be a function depending on x, but let's think of k as a constant and as a positive constant. And then in two variables, our equation will be first derivative with respect to first independent variable squared plus first derivative with respect to the second independent variables, and both derivatives are squared, right? So we have gradient and we have magnitude of this gradient equals to k. And this, let's take this as initial conditions. So using notations that we've been using before, if ux is we call p, uy q, then our equation can be written in the form p squared plus q squared minus k equals 0, or Hamiltonian will be h p squared plus q squared minus k. Right, in this case we even don't have dependence on independent variables. Right, so here I just wanted to remind us the Hamiltonian equations. So I just copied them here, and I copied in addition the equation for u. Right, we said that all of them describe all of them just are characteristic equations. And now let's specify the Hamilton's equation for our case. So we have here dx dt. So let's take first our first variable, which is x, this curve x, dx dt. What is hp? hp would be 2p, right, if we differentiate with respect to p. And then second variable, we call it y, so we write dy dt equals, for the same reason, it will be 2q, right? So we have this equation, and equation for p, we have to write negative h. Hamiltonian must be differentiated with respect to x, but since we don't have x here, then dp dt would be 0 and dq dt would be 0, right? The whole vector pq, when we differentiate, is 0. And what is our equation for u? Let's write it here. So for u, we have du dt equals, and here we must have dot product, p and hp. So p, we write, when this is differentiated with respect to p, it will be just 2p, so p times 2p plus second component of this vector p. So again, so here p is a vector, here in the example, our vector p corresponds to pq. Right, so here's a vector. And then we will have q times 2q. So finally we can rewrite it as du dt equals 2p squared plus q squared. But we have our equation, so we can simplify, since p squared plus q squared equals k. So instead of this, we can write du dt equals 2k. This equation is much easier to solve then. Right, and now let's talk about initial conditions. So these were equations, right? So we specified all of the differential equations, and I copied this equation for you here in blue. So now all of our characteristic equations are here. A Hamilton's equation plus equation for you. And now let's write down initial conditions. So initial conditions, first three, we write in the same manner as we did for quasi-linear equations. So we have x of 0s would be s, right? We have it here. Y at 0s would be 2s, and u at 0s is 1, right? We wrote what we have here, and now we need to get initial conditions for p, and we will proceed the same way as we did in the previous example. So we take our equation, this, and differentiate with respect to x, because it depends on x. So then, when we differentiate with respect to x, so we differentiate u with respect to first component will be du dx, plus u with respect to second is y, du dy, times chain rule derivative of 2x with respect to x, which is 2, and derivative of 1 is 0. So in our notations pq, ux, we have p, and here we will have this equation p plus 2q equals to 0. So we prepared to write down initial conditions for p and q, at least one of them. One of them is ready, right? We can write that p at 0s plus 2q at 0s equals to 0. This is our equation we got. And the second equation is just our differential equation. It will be p squared at 0s plus q squared at 0s equals k. So now we have our system to define initial conditions for p and q. We can solve for instance, first equation and say that P equals negative 2Q, and then plug this into the second equation. So then here we will have here it will be just 4Q and plus 1Q squared, so 5Q squared equals K. And then we want to solve for Q, but when we take in square root, we can have plus or minus. Right, so plus or minus, so in this problem it indicates that there is no uniqueness. And I have chosen minus because I want to have P with plus, but for no reason absolutely. So just to choose something, and then if I choose minus, then from this equation P would be initial condition to K over 5, and this is just from initial condition when T equals to 0. And now we have to look at our Hamilton's equation, dp dt, and we can see that there is no dependence on T, so those actually would be our solutions for P and Q. And so how we can explain non-uniqueness? Suppose this is our initial front light, and it can propagate if P and Q related to say velocity vector, then it can propagate in this direction, or it can propagate in the opposite direction. So that's how we can explain non-uniqueness from physical viewpoint. And then, so we found P and Q, right? So now we can finish solving our Hamilton's equation by finding x and y. For x we have dx dt equals to P, and since P is this, now this will be 4 square root of K over 5, and then we integrate, it will be the same constant times T plus function of S. And then we use initial conditions. X at 0 must be equal to S, and when T is 0, this disappears, so it means that F1 equals to S. So the final formula for X would be S plus 4 square root of K over 5 times T. So this is our formula for T, and in a similar fashion we solve equation for Y. dy dt equals 2Q, so this is Q2, and we integrate, it will be the same constant times T plus F2 of S, and initial condition tells us that it must be 2S when T is 0. So when T is 0, this disappears, so this is 2S minus 2 square root of K over 5 times T. So this is our final formula for Y. And then our Hamilton's equations are solved. We need to solve equation for U, which is also a simple equation, du dt equals 2K, and when we integrate we have 2KT plus F3 that depends on S, and initial condition tells us that function F3 equals to 1. I copied equation for U here, so for U we have 2KT plus 1, and I copied equations for X here and Y here. So now we have all of the equations together that we need, and what we can notice that if we look at this equation for X and Y, we can see that our characteristics are lines. And also we can notice that here dp dt dq dt equals 0. So what's happening in the system describes the profile traveling with constant speed along straight lines, right? So it's related to light propagation. And Okay, so we have this here, and then we want to find s and t in terms of x and y, so we can give this equation name E1, to the second equation E2. If we take 2E2 and 2E1 and subtract E2, we will get 2x minus y, and then here we will get 10 square root of k over 5t. And to have the second convenient equation written in convenient form, we will take E1 plus 2E2, and then we will have x plus 2y's equals 5s. And from here we immediately can get t, which we need for u. U doesn't depend on s, but just to show that it is still possible, that is easy, we find equation for s. And now we just plug the expression for t that we found into equation for u, and we will get 1 plus 2k, and then expression for t, this constant, and times 2x minus y. And then we slightly simplify, and we find the answer, we find expression for our function u in terms of x and y, and that would be 1 plus square root of k over 5 2x minus y, and it was a solution, simple example of solving Cauchy problem for the eikonal equation. And I want to make a final remark for this lecture. It's about one of the equations that is important, very important in calculus of variations, and it is related to our Hamilton's equations and to Hamiltonian that we have discussed, and this is called the Hamilton-Jacobi equation. So if you remember, we've been talking just about equations of this type when we have no dependence on u. So we have h of xp, and x is n-dimensional vector and p is n-dimensional vector. So now let's look at this equation. I call it h tilde. So h tilde is q plus h of xp. So what is the change of notations? I should put it here. So now instead of just n-dimensional n independent variables, we add one more independent variable, so we have x plus we have n plus 1 variables. So typically this variable that I call here y, it's related to time, it stands for time. So we have derivative with respect to time plus everything that depends on partial derivatives. And I call this new vector h tilde, right? And then my vector of partial derivatives now will get another component, so we will call it vector p that we have, and plus one more component, and plus first component, so we call this combined vector p tilde. And then in this form our equation with h tilde would be of at the same form as we had before. So it will be h tilde of x tilde p tilde equals 0. And this equation is called Hamilton-Jacobi equation, and h tilde here is q plus the old h that we have. And as I mentioned, it's related to calculus of variations, and in the Evans book it's written in section 3.3. Maybe we will be back to this equation in the second part of the course. And so now what our characteristic equations will look like. So here I just copied again the system of characteristic equation for general nonlinear equation in the form that we had before, f of x u p equals 0, right? And now I am specifying this system for our equation. So here we differentiated with respect to p. Instead of f, we have now h tilde, but for the first n variables, we will have the x dt equals hp, because this one would be 0. And for the, so it will be the same equation that we had before. And for the last one, the variable y, right, last independent variable, we will have, when we differentiate with respect to our p tilde vector, we will have derivative with respect to q, so we will have 1. And then dp dt, we differentiate, so for the first n components, we will have negative f of x, it will be negative h of x, right? So it will be again the same h without tilde, and for the last equation, we will have dq dt equals 0, right? Because there is no dependence, explicit dependence on y. And for u, we had this equation p hp, right? For the, if we write first n components, and for the last one, it will be q, and derivative of this with respect to q is 1, so it will be just q times 1. And now we can rewrite it not using q, because our equation, our original equation is q plus h equals 0, right? H tilde equals 0, it means q plus h equals 0. So I put it here, q plus h equals 0 means that q equals negative h. So then our equation for u is written p hp minus h, so everything in terms of h. And again, you can see that here these two equations are simple, right? So we can integrate them separately, but mainly we again have the Hamilton's equations. So this new Hamilton-Jacobi equation is related to the same Hamilton's equations with the same Hamilton h. Just we have to specify how to compute here. Thank you.